Out there, drifting between the stars, hidden within vast clouds of interstellar plasma, something is speaking, and we don't know what it is. Mysterious signals, crackling through the cosmos, reach our telescopes as faint whispers from the void. Some last mere milliseconds, others repeat in patterns we can't decipher, but all of them defy easy explanation. Could these be natural phenomena, the universe's own strange music, or might they be something more, hints of intelligence beyond our own? For decades, scientists have traced these enigmatic bursts, each one a cosmic riddle written in radio waves, and every answer we think we find only leads to deeper questions. Imagine standing under a clear night sky, gazing up at the infinite darkness, and knowing somewhere out there forces we can barely comprehend are sending signals across light years. Some of these transmissions are so powerful, they outshine entire galaxies for the briefest moment before vanishing without a trace. Others pulse with eerie regularity, like a heartbeat from the depths of space. What creates them? Colliding stars, rogue black holes, or could they be deliberate, a message not meant for us but echoing through the universe all the same? The possibilities stir something primal in us, that mix of awe and unease, the thrill of the unknown calling just beyond our understanding. Today, we're diving into 25 of the most baffling signals ever detected, each one a story written in energy and mystery. From the infamous WOW signal to strange repeating bursts from deep space, these aren't just random noise, they're pieces of a puzzle that could rewrite our place in the cosmos. Some might be natural, some might not be, and that's the most thrilling part. So let's unravel these interstellar enigmas together, because the universe is speaking and it's time we listened. Of all the signals ever captured from the depths of space, none has captured our imagination or fueled more debate than the WOW signal. It all began on a quiet August night in 1977 when Ohio State University's Big Ear radio telescope picked up something extraordinary. For 72 seconds, a burst of radio waves blazed across the receiver, so intense that astronomer Jerry Amon famously circled the reading on the printout and scribbled WOW next to it in red ink. That single word gave the signal its name, but the mystery behind it has lingered for nearly half a century. What made this transmission so special? For starters, it wasn't random static. The signal hit a precise frequency, 1420 MHz, a quiet band where natural cosmic noise is minimal, making it ideal for interstellar communication. It matched the signature we'd expect from an artificial source, rising and falling in strength exactly as a distant transmission would as Earth's rotation swept the telescope's gaze across the sky. And then, just as suddenly as it appeared, it vanished. Despite repeated efforts, no one has ever heard it again. The signal seemed to originate near a group of stars in Sagittarius, but pinpointing its source has been impossible. Some argue it could have been a comet's hydrogen cloud reflecting sunlight, though that theory crumbles under scrutiny. The known comets in the area at the time didn't match the signal's location. Others suggest a rogue natural phenomenon, like a pulsar glitching in an unusual way, but pulsars repeat, and the WOW signal was a one-time event. Then, of course, there's the haunting possibility. What if it wasn't natural at all? Decades later, with no definitive explanation, the WOW signal stands as a cosmic ghost, a fleeting whisper that defies categorization. It's a reminder of how much we still don't understand, and how the universe might be hiding conversations just beyond our reach. Was it a cosmic accident, a malfunctioning satellite, or something far more profound? Until we catch it again, that handwritten WOW remains our only clue. If the WOW signal was a cosmic shout, then the Lorimer Burst was a scream, brief, violent, and utterly bewildering. It arrived without warning in the archives of a radio telescope survey from 2001, though no one noticed until 6 years later when astronomer Duncan Lorimer and his student David Narkevic sifted through old data. What they found was a single spike of radio waves so powerful, it lasted just 5 milliseconds but packed more energy than the sun emits in a month. This wasn't just a blip in the noise, it was a celestial explosion written in light, and it came from somewhere far beyond our galaxy. The numbers alone are staggering. The burst originated roughly 3 billion light-years away, meaning whatever produced it happened when Earth was barely a third of its current age. To reach us across that distance, the signal must have been unimaginably energetic, equivalent to 500 million suns unleashing their power in an instant. Yet there was no afterglow, no visible explosion or remnant left behind in the sky. Just that one fleeting burst, as if the universe itself had flicked a cosmic switch on and off. What could possibly generate such a short, intense flash? Normal astrophysical events like supernova or colliding neutron stars tend to leave traces, lingering radiation or debris we can study. The Lorimer Burst left nothing. Pulsars, those rapidly spinning neutron stars that beam radio waves like lighthouses, usually pulse with predictable rhythms. This was a one-off. Even the most extreme cosmic phenomena struggle to explain something so brief yet so powerful. Some theorists suggested exotic possibilities, a hyperflare from a magnetar, a collapsing black hole, or even cosmic strings, hypothetical defects in spacetime itself. Others cautiously floated the idea of artificial origins, though with no repeating pattern or structure. Even that remains pure speculation. Then came the real twist. For years, the Lorimer Burst stood alone, an outlier so strange that skeptics wondered if it might be terrestrial interference, a rogue satellite or a glitch. But then more bursts surfaced, each one different, each one defying easy explanation, yet sharing that same signature of impossible energy compressed into milliseconds. Suddenly, the Lorimer Burst wasn't just a mystery. It was the first chapter in a much bigger story. To this day, no one knows what caused it, but its discovery shattered assumptions about the universe's radio whispers. If such titanic, fleeting signals are out there, hidden in the static, what else might we be missing? The Lorimer Burst taught us to expect the unexpected, because sometimes the cosmos speaks in shouts, not whispers. The SHGb02+14a anomaly is the kind of signal that makes astronomers double-check their equipment, then triple-check it. Discovered in 2003 by the SETI Institute's Project Serendip, this repeating radio whisper seemed to tick all the boxes for an artificial transmission. It pulsed at a frequency of 1,420 MHz, the same quiet band as the WOW signal, and it kept coming back, not just once, but 4 separate times over several years. But here's where things get strange. Unlike a steady beacon from a distant civilization, this signal drifted. Its frequency shifted ever so slightly with each detection, as if the source were moving at breathtaking speed or wobbling unpredictably through space. That drift sent scientists spiraling into debate. Natural objects like pulsars emit stable frequencies, locked into place by the laws of physics. A drifting signal suggests something else entirely. Perhaps a transmitter mounted on a planet with a wobbling orbit, or a spacecraft hurtling through the void. But the numbers didn't quite add up. The frequency shift implied movement at nearly 130 kilometers per second, far faster than any known exoplanet. Even stranger, the signal appeared to originate from a patch of sky near the Pisces constellation, a region eerily empty of stars or galaxies. No obvious cosmic landmarks, no known planets, just an eerie radio flicker from what seemed like nowhere. Skeptics were quick to offer alternatives. Could it be interference from Earth's own satellites, their signals bouncing off the ionosphere in unpredictable ways? Yet SETI's own analysis ruled out most terrestrial sources. Others proposed exotic natural phenomena, like a never-before-seen type of neutron star spinning unevenly, its radio beams twisting like a lighthouse in a storm. But no such object has ever been observed, and without a visible counterpart in the sky, the theory remains pure speculation. Then there's the haunting detail that keeps this mystery alive, the signal's repetition. Random cosmic noise doesn't usually revisit the same spot at the same frequency. The fact that SHGb02+14a reappeared, however faintly, suggests structure, a pattern that feels almost intentional. But with no further detection since 2004, the signal has faded into silence, leaving us with more questions than answers. Was it a glitch? A fluke of astrophysics, or a fleeting hello from something, or someone we can't yet comprehend? For now, SHGb02+14a lingers in the annals of cosmic mysteries, a ghostly reminder that the universe often teases us with clues just beyond our grasp. It's the kind of enigma that keeps astronomers awake at night, staring at static-filled screens, wondering if the next blip in the noise might finally reveal the truth. Most cosmic signals fade into oblivion after a single burst, but not FRB 121102. This anomaly didn't just flash once, it erupted again and again, defying every expectation scientists had about fast radio bursts. When it was first detected in 2012 at Puerto Rico's Arecibo Observatory, it seemed like another fleeting mystery. Then, in 2015, something extraordinary happened. The signal repeated. Not just once, but multiple times, in irregular bursts that crackled across 3 billion light-years of space like a malfunctioning interstellar transmitter. Suddenly, astronomers had their first clue that these bizarre flashes might not be cosmic accidents after all. Pinpointing its origin only deepened the intrigue. FRB 121102 wasn't lurking in some anonymous void. It was nested inside a tiny, turbulent dwarf galaxy, a place where stars are born in violent bursts. This wasn't the quiet, orderly neighborhood of older galaxies. It was a stellar nursery, crackling with the energy of young magnetars, neutron stars with magnetic fields so intense they could strip atoms apart from thousands of kilometers away. The galaxy's chaotic environment made magnetars a prime suspect. Imagine a spinning magnetar, its crust buckling under magnetic forces trillions of times stronger than Earth's, unleashing sporadic quakes that ripple through space-time. These starquakes could theoretically produce the erratic bursts we observe, but there's a catch. No known magnetar emits radio bursts this powerful or this frequently. That gap in understanding fuels wilder theories. Some researchers speculate about advanced civilizations harnessing cosmic-scale energy, perhaps powering interstellar probes with beams so intense they're detectable across the universe. The idea isn't as far-fetched as it sounds. Humanity's own radio and radar signals already leak into space. A civilization millennia ahead of us might deliberately broadcast, or even use focused energy to propel ships, creating unintentional flares as a byproduct. Of course, skeptics counter with Occam's razor. The simplest explanation is usually right. Yet, simple feels inadequate when faced with a signal this bizarre. Then came the twist no one saw coming. In 2017, astronomers caught FRB 121102 in the act, capturing not just radio waves but a flicker of polarized light. The signal's waves were twisted, a phenomenon called Faraday rotation, suggesting they'd passed through an extraordinarily powerful magnetic field. This was the smoking gun linking the bursts to a magnetar's extreme environment. But even that revelation left puzzles unsolved. Why do some bursts cluster together while others vanish for months? What triggers them? And why, out of all the magnetars we've observed, does this one dwarf galaxy host such a prolific repeater? The most tantalizing possibility is that FRB 121102 isn't alone. Since its discovery, dozens more repeating bursts have surfaced, each with its own quirks. Some are erratic, others pulse with near-clockwork precision. Together, they hint at a spectrum of cosmic phenomena we're only beginning to decode. Whether born from dying stars or something far stranger, These repeating whispers from the void challenge our assumptions about the universe's quiet corners and remind us that some mysteries refuse to stay silent. The BLC-1 signal was the kind of discovery that sends astronomers scrambling for their notebooks and conspiracy theorists into overdrive. Detected in April and May of 2020 by the Parkes Radio Telescope in Australia, this narrowband radio whisper seemed tailor-made to ignite the imagination. At exactly 982 MHz, a frequency conspicuously free of cosmic noise, the signal appeared to originate from Proxima Centauri, the closest star system to our own, just 4.2 light-years away. Even more tantalizing, orbiting that star is Proxima b, a rocky exoplanet nestled in the habitable zone where liquid water could theoretically exist. For a brief, electrifying moment, it felt like humanity might have just overheard our cosmic neighbors. What set BLC-1 apart wasn't just its origin. The signal exhibited a telltale drift, its frequency shifting subtly over time, exactly what you'd expect if it came from a planet orbiting a star. Unlike the random crackle of astrophysical phenomena, this was a clean, narrowband transmission, the kind produced by human-made satellites or, hypothetically, an alien transmitter. The team behind the Breakthrough Listen project, which hunts for technosignatures, cautiously dubbed it a candidate signal, the most promising one since the WOW. Signal news leaked, headlines blared, and for the first time in decades the public dared to wonder, had we finally found proof we weren't alone? But science thrives on skepticism, and the euphoria was short-lived. As researchers pored over the data, cracks began to show. The signal never repeated, despite exhaustive follow-up observations. Then came the kicker. Further analysis revealed a suite of look-alike signals at nearby frequencies, all bearing the unmistakable fingerprint of human-made interference. These imposters shared the same drift pattern as BLC-1, suggesting a common origin, likely a malfunctioning satellite or a ground-based transmitter whose signal had bounced off some surface, creating a deceptive echo. The final nail in the coffin, BLC-1 frequency coincided with known radio interference bands used by earthly technology. Yet even in dismissal, the signal left a trail of unanswered questions. Why did it appear to originate from Proxima Centauri's precise location, not just a random patch of sky? Why did it mimic the drift of a planetary signal so convincingly? Some scientists argue the alignment was pure coincidence, a cosmic prank played by unlucky odds. Others, though conceding the likelihood of human interference, quietly point out that we've never fully ruled out the possibility of something stranger. After all, Proxima Centauri is a flare star, prone to violent eruptions of radiation. Could some exotic stellar phenomenon mimic an artificial signal? Or might a civilization, if it existed there, purposefully broadcast on frequencies we use, knowing we'd notice? The aftermath of BLC-1 was a masterclass in scientific rigor and humility. It reminded us how easily hope can outpace evidence, but also how even false alarms push technology forward. Breakthrough Listen refined its detection protocols, adding layers of verification to weed out earthly noise. Meanwhile, Proxima Centauri remains a prime target in the search for life, its mysteries undiminished by a single tantalizing false start. Because here's the truth, the universe is vast, and signals like BLC-1, whether born of human error or cosmic chance, are the breadcrumbs that keep us searching. One day, one of them might just lead us home. In the summer of 2016, a Russian radio telescope known as Ratan 600 caught something extraordinary, a signal so strong it seemed to shout across the cosmos. The transmission originated from the direction of HD 164595, a sun-like star 94 light-years away, and it arrived with a burst of energy 11 times more intense than anything natural processes should produce. For a fleeting moment, astronomers held their breath. This wasn't just another blip in the static. It was a signal that defied expectations, sparking whispers of "could this be it?", the moment we dreamed of for decades. What made this signal so unusual wasn't just its strength. It pulsed at a wavelength of 2.7 centimeters, a frequency often used by military and satellite communications here on Earth. That eerie familiarity raised immediate questions. Could this be a stray transmission from one of our own spacecraft, bouncing off space debris or echoing back to us in some unexpected way? The research team scrambled to rule out terrestrial interference, checking satellites, aircraft, and even ground-based transmitters. Nothing matched. The signal appeared to come from deep space, and it vanished just as abruptly as it arrived, leaving no trace behind. Then came the real twist. SHGb02+14a wasn't just any star. It hosts at least one known planet, a Neptune-sized world orbiting too close to be habitable. But where there's one planet, there could be others, lurking undetected in the star's Goldilocks zone. The thought was irresistible. If an advanced civilization existed there, might they be broadcasting? The signal's power only fueled speculation. To reach Earth with such intensity, any intentional transmission would require energy on a staggering scale, equivalent to harnessing the entire output of a star. That's a feat beyond our technology, but not necessarily beyond imagination for a civilization even a few centuries ahead of us. Skeptics, of course, rushed to offer alternatives. Perhaps it was a rare cosmic maser, a naturally occurring amplification of radio waves by interstellar gas clouds. Or maybe a microlensing event where the gravity of a passing object bent and magnified a distant signal by chance. Yet neither explanation fully accounted for the signal's precise frequency or its sudden disappearance. The most telling detail, despite repeated observations, the signal never returned. It became a cosmic one-hit wonder, leaving astronomers with a tantalizing question mark. Years later, the Rattan 600 mystery remains unsolved. Some insist it was a technical glitch, a ghost in the machine. Others quietly point out that the universe rarely serves up coincidences this provocative. Whether a fleeting natural phenomenon or something far more profound, this signal is a reminder of how little we still know about the whispers filling the void. And with every unexplained burst, the cosmos nudges us to listen closer because the next signal might not vanish without a trace. For years, the Parkes Observatory in Australia played host to a cosmic mystery until researchers realized the culprit wasn't cosmic at all. Meet the Puritans, bizarre radio bursts that mimic the elusive fast radio bursts from deep space, only to reveal a far more mundane and strangely poetic earthly origin. First detected in the late 1990s, these signals shared uncanny similarities with FRBs, fleeting, intense, and seemingly from random directions in the sky. But unlike true FRBs, which arrive from billions of light years away, the Puritans had a habit of striking only during business hours and always within the observatory's line of sight. The name itself hints at their elusive nature. In medieval mythology, a Puritan is a winged stag that casts the shadow of a human, blending the familiar with the uncanny. Scientists adopted the term for these signals precisely because they seem to wear two faces, cosmic in appearance, but with hidden terrestrial roots. For over a decade, they fooled even seasoned astronomers, sparking debates over whether they represented a new class of astrophysical phenomenon or faulty equipment. Then, in 2015, a breakthrough came from an unexpected source, the observatory's kitchen. Researchers noticed Puritans only appeared when staff used the microwave oven, specifically when someone opened the door mid-cycle. The burst of radiation escaping the microwave, distorted by the telescope's sensitive receivers, created a signal that looked interstellar but was as local as a reheated lunch. The discovery was equal parts hilarious and humbling. Here was a mystery that had consumed years of research, only to be solved by a malfunctioning kitchen appliance. But the Puritans' legacy isn't just a punchline. They taught astronomers a vital lesson about the perils of cosmic pareidolia, the human tendency to see patterns where none exist. Yet even this explanation left lingering questions. Why did the signals appear to come from different directions? The answer lay in the telescope's design. Parkes' massive dish reflects radio waves not just from space but from the ground, and a microwave's burst bouncing off nearby hills or buildings could masquerade as a celestial event. This revelation forced scientists to refine their detection methods, implementing stricter filters to weed out terrestrial interference. The Puritan story is a reminder that the universe's greatest puzzles sometimes begin and end closer to home. They're a cautionary tale about the seductive allure of mystery and how even the most tantalizing signals might just be the universe's way of pranking us. But in a way, that's the beauty of science. Sometimes the answers are stranger than the myths we invent to explain them. Deep in the constellation Sagittarius, hidden within a swirling cloud of interstellar dust known as the glimpse region, astronomers spotted something that shouldn't be there. A flicker of infrared light so peculiar it defied every known natural explanation. Named after the survey that discovered it, Glimpse C01, this signal wasn't just unusual, it was impossible. Unlike the steady glow of stars or the diffuse warmth of cosmic dust, this light pulsed with bizarre spectral features, as if some unseen force were bending the very rules of physics. The more researchers studied it, the more it seemed to whisper a tantalizing question. What if this isn't natural at all? Infrared signals usually tell straightforward stories. Young stars heat surrounding dust, while dying stars shed glowing envelopes of gas. But Glimpse C01 matched none of these. Its spectrum, the fingerprint of its light, showed sharp, unnatural dips at specific wavelengths, as if something were selectively absorbing energy in precise, artificial bands. Even stranger, the signal appeared to originate near the center of our galaxy, a chaotic region packed with stars, black holes, and swirling plasma. Yet there was no visible object at its location. No star, no nebula, nothing but an eerie glow where nothing should exist. Theories spiraled. One camp argued for exotic physics, perhaps an unknown type of interstellar dust with bizarre light-scattering properties, or even a rogue black hole's accretion disk behaving in unprecedented ways. Others dared to voice the unthinkable. Could this be evidence of a Dyson swarm, a hypothetical megastructure built by an advanced civilization to harvest a star's energy? The idea isn't as wild as it sounds. Freeman Dyson, the physicist who first proposed such constructs, suggested they'd emit waste heat in the infrared, exactly the wavelength of the glimpse signal. A partial swarm, still under construction, might explain the irregular spectral features like gaps in a cosmic jigsaw puzzle. Skeptics, of course, countered with Occam's razor. The universe is vast, and we've barely scratched the surface of its phenomena. New types of cosmic objects are discovered regularly. Why leap to alien megastructures? Yet even they struggled to explain the signal's precision. Natural processes tend to be messy, governed by chaotic interactions. Glimpse C01's spectral lines were too clean, too deliberate, as if engineered rather than born from random cosmic forces. Then came the twist. Further observations revealed another layer of strangeness. The signal varied over time, flickering in ways that defied even the Dyson swarm hypothesis. Some researchers proposed a middle ground, perhaps a natural object behaving in ways we've never seen, like a neutron star wrapped in an exotic magnetic field, or a quasar's echo bouncing off an invisible cloud of particles. Others wondered if we were witnessing the aftermath of a colossal, unseen collision, a cosmic car wreck scattering debris that just happened to glow in this peculiar way. Years later, the mystery endures. Glimpse C01 remains an enigma, a cosmic Rorschach test where every scientist sees something different. Whether it's proof of alien engineering or merely a new chapter in astrophysics waiting to be written, one thing is certain: the universe still holds surprises that defy our boldest theories. And sometimes the strangest signals aren't just messages from the void, they're mirrors, reflecting back how much we have yet to learn. KIC 8462852, better known as Tabby's star, doesn't just flicker. It plummets. Imagine a sun-like star 150 parsecs away that occasionally dims by up to 22%, as if something colossal were passing in front of it. Not a planet, not a comet, not even a swarm of comets. We're talking about drops in brightness so extreme they defy every conventional explanation. And when astronomers turned their radio telescopes toward this cosmic oddity, they caught whispers of something even stranger, anomalous signals crackling through the interstellar plasma around it, as if the star itself were humming a tune we couldn't quite decipher. The first hints came from Kepler, the planet-hunting telescope, which spotted Tabby's star's erratic behavior between 2009 and 2013. Normal stars dim in predictable, rhythmic ways when planets orbit them, but Tabby's star's dimming was chaotic. It dropped brightness at irregular intervals, sometimes for days, other times for weeks, with no discernible pattern. One particularly dramatic event, dubbed Elsie, saw the star's light vanish by 15% over just 2 days. Then, just as mysteriously, it returned to normal. The universe doesn't do that without a reason, and the hunt for answers led to 2 competing camps, those who blamed natural cosmic phenomena and those who dared to wonder if we were seeing something built. Natural explanations piled up fast. Maybe it was a vast cloud of dust and debris, remnants of a shattered planet or a catastrophic collision. But dust scatters light in predictable ways, and Tabby's star's dimming didn't match those models. Others proposed a swarm of megacomets, hundreds of thousands of them, trailing enough gas and ice to blot out a star. The problem, even that couldn't explain the star's long-term secular dimming. Observations showing it had faded by nearly 3% per century, a decline no known stellar process should cause. Then came the plasma angle. Some theorists suggested a magnetically trapped bubble of charged particles, a stellar storm so dense it could intermittently eclipse the star. Plasma, after all, can twist light in strange ways, and if it were turbulent enough, it might account for the erratic dips, but here's where the plot thickens. Radio observations revealed another layer to the mystery. The star's surroundings crackled with low-frequency emissions, the kind you'd expect from intense plasma activity. Yet the signals weren't just random noise, they had a faint structure, almost like the hum of machinery. That's when the whispers of artificiality began. The most controversial theory, a Dyson swarm, a vast array of energy harvesting megastructures built by an advanced civilization. Such a construct wouldn't be a solid shell, but countless orbiting panels or satellites, each catching a fraction of the star's light. Their uneven arrangement could explain the sporadic dimming, while their operation might generate detectable electromagnetic signatures. Skeptics bristled at the leap, and rightly so. Extraordinary claims require extraordinary evidence, and Tabby's star hasn't coughed up anything definitive. Yet the allure of the idea persists because it fits not perfectly but hauntingly. If aliens weren't the answer, then what was a new class of stellar behavior, a cosmic catastrophe we've never witnessed before? Every time we think we've pinned Tabby's star down, it throws another curveball. In 2017, it dimmed again, and this time telescopes caught it in multiple wavelengths. The result, the dips weren't uniform. Some colors of light were blocked more than others, a fingerprint inconsistent with solid objects but eerily compatible with diffuse, engineered materials. Years later, Tabby's star remains a riddle wrapped in a mystery. It's taught us humility, showing how much we still don't know about the cosmos. Whether the answer lies in undiscovered physics, an unimaginable natural event, or just maybe something beyond our current understanding, one thing's certain: this star refuses to be ignored. It's a reminder that the universe doesn't owe us neat explanations, and sometimes the most profound discoveries begin with a single, unblinking question: what the heck is that? Canada's CHIME telescope has become one of the most prolific hunters of fast radio bursts, But buried within its growing catalogue of detections lies a subset of signals so strange, they've rewritten the rulebook on what we thought these cosmic flashes could do. Unlike the isolated blips or even the repeating bursts we've seen before, these chime oddities arrive with patterns that defy physics as we know it, starting with their dispersion measures, the telltale fingerprints of how much intergalactic plasma they've traversed. Normally, this value should increase predictably with distance, acting like a cosmic odometer, but chime outliers flip that assumption on its head. Some exhibit dispersion measures too low for their estimated locations, as if they've taken shortcuts through the universe. Others pulse with such tightly clustered dispersion values, it's as though they're all passing through the same mysterious patch of space, a celestial toll booth we can't see. Take FRB 181204, for example. This burst didn't just challenge models, it mocked them. Its dispersion measure suggested a source relatively close by, yet its energy profile matched bursts from billions of light years away. Even stranger, it was surrounded by a cluster of similar signals, all with nearly identical dispersion measures but arriving months apart. If these bursts came from the same object, why wouldn't their dispersion values drift over time as the universe expanded? One theory points to an unseen structure, a vast ionized filament of gas threading between galaxies, bending radio waves in ways we don't yet understand. Another, more radical idea proposes that the bursts are being lensed, magnified and distorted by an invisible cosmic sieve, perhaps a rogue black hole's gravity warping their path to Earth. Then there's the puzzle of periodicity. While most FRBs fire off at random, chime has catalogued bursts with eerie rhythmic precision. FRB 180316, for instance, repeats every 16.35 days like clockwork, 16 days of silence, then a frenzied window where it spits out multiple bursts before going quiet again. No known celestial object behaves this way. Neutron stars have regular spins, but their pulses don't turn on and off in scheduled intervals. Binary star systems can produce periodic signals, but none match this exact timetable. The leading explanation involves a highly magnetized neutron star orbiting another massive object, possibly a black hole, with its magnetic field lines snapping and reconnecting like overstretched rubber bands at precise points in its orbit. But even that's a shaky fit, requiring conditions so specific they border on the improbable. The real shock came when chime detected bursts with two distinct dispersion measures within a single event, as if the signal had split in transit, with one half taking a scenic route through extra plasma. This isn't just unusual, it's theoretically forbidden. Radio waves traveling through space should disperse uniformly. The only way this could happen is if something in the signal's path, a supernova remnant, a plasma-rich galaxy cluster, or even an unseen dark matter structure, acted like a prism, splitting the burst into separate strands. Yet when astronomers searched the suspected regions, they found nothing, no dense nebula, no intervening galaxy, just empty space where the laws of physics seem to momentarily glitch. What makes these chime anomalies so thrilling isn't just their strangeness, it's how they expose the gaps in our cosmic maps. Each one is a breadcrumb leading to phenomena we've either overlooked or never imagined. Could they be traces of exotic physics, like decaying cosmic strings or collisions between theoretical particles? Might they hint at hidden dimensions, their signals taking detours through folds in space-time we can't perceive? Or in the quietest corners of scientific discourse, could they be evidence of something engineered beacons or propulsion signatures from civilizations playing by rules we haven't discovered yet? The chime catalog keeps growing, and with every new oddity, the universe feels a little less predictable. These bursts aren't just mysteries, they're invitations to rethink everything we thought we knew about the interstellar medium, the nature of radio waves, and the invisible scaffolding of the cosmos. They remind us that for every answer we find, the universe has a dozen more questions waiting in the static. In the quiet pre-dawn hours of August 6, 1967, Cambridge astrophysicist Jocelyn Bell Burnell was scanning reams of radio telescope data when she spotted something that made her pencil freeze mid-calculation. Streaking across the chart paper was a series of pulses so precise they looked engineered, one burst every 1.337 seconds with atomic clock regularity. The signal, dubbed LGM-1 for Little Green Men, sent shockwaves through the scientific community. For weeks, the team dared not speak openly about their discovery, quietly considering the unthinkable. Had they just intercepted an alien transmission? What made LGM-1 so unnerving wasn't just its rhythm, it was the physics behind those pulses. The signal originated from interstellar plasma, that diffuse sea of charged particles filling the space between stars. Under normal conditions, plasma emits radio waves in chaotic bursts like static from a storm. But LGM-1 signal was sculpted into sharp peaks, as if some cosmic force were focusing the plasma's energy like a laser beam. The leading natural explanation, a rotating neutron star, seemed almost as fantastical as alien beacons at the time. How could a collapsed stellar core, barely 20 kilometers across, whip around hundreds of times per second while blasting focused radio waves across light years? The answer lay in plasma's dance with extreme magnetism. When a massive star collapses into a neutron star, its magnetic field compresses into a trillion Gauss monster, strong enough to rip electrons from atoms and accelerate them to near light speed. These charged particles spiral along magnetic field lines, and where those lines converge at the star's poles, the plasma emits synchrotron radiation, focused beams of radio waves sweeping through space like lighthouse beams. Each time a beam swept across Earth, Bell's telescope registered another pulse. What seemed like an intelligently timed signal was actually plasma physics pushed to its limits, a natural maser operating on cosmic scales. Yet even this revelation left puzzles. Some pulsars, like the Black Widow system, exhibit plasma interactions so violent they eclipse the pulsar entirely for periods. Others, like the zombie pulsar PSRB 1257+12, stop pulsing for years before inexplicably restarting. These anomalies show how plasma's behavior around compact objects can mimic patterns we'd associate with technology: erratic shutoffs, frequency drifts, even signal harmonization when multiple pulsars interact. Modern astronomers now recognize these as magnetospheric phenomena, but to Bell's team in 1967, the line between natural wonder and alien engineering was thrillingly thin. The legacy of LGM-1 endures not just as a cautionary tale about jumping to extraterrestrial conclusions, but as proof that nature often outdoes our wildest imaginations. Pulsars taught us plasma can sculpt radio waves into signals rivaling anything we could engineer, and that the universe has a knack for dressing its most exotic physics in the guise of something familiar. Every time a new mystery signal emerges today, LGM-1 whispers a reminder: sometimes the truth is stranger than little green men. On September 22, 2018, Earth's orbital telescopes caught a flash of gamma rays so powerful it should have lit up the sky like a second sun, except no one saw it coming. Dubbed the Vela Jr. anomaly, this burst wasn't just unusually energetic, it was invisible. While gamma-ray bursts typically announce their arrival with an afterglow visible across multiple wavelengths, X-rays, ultraviolet, even visible light, this one left no trace beyond its initial detonation. It was the cosmic equivalent of a firework exploding in a pitch-black room. All concussion, no light. Theories erupted immediately. Had astronomers witnessed the birth of a black hole in a plasma-saturated corner of space, or something far more exotic, a collision of dimensions, a crack in space-time itself? The burst originated near the Vela constellation, home to the famous Vela supernova remnant, but this event was separate, younger, stranger. Its gamma-ray signature pointed to a cataclysm roughly 800 million light-years away, yet follow-up observations by every major telescope turned up nothing. No fading ember of a dying star, no swirling debris from neutron stars colliding, just silence where there should have been chaos. This absence became the mystery. Gamma rays don't emerge from nowhere. They're the universe's most violent tantrums, usually triggered by supernova or merging compact objects. For a burst this strong to leave no aftermath was like a bomb detonating without a crater. One explanation points to plasma's ability to cloak cosmic violence. Imagine a star collapsing into a black hole, but instead of exploding outward, its energy funnels into a jet of ultra-relativistic plasma-charged particles moving at 99.9% the speed of light. If that jet were perfectly aligned with Earth, we'd see the gamma rays as a narrow beam, while the surrounding optical light gets smothered by the plasma's own opacity. It's a cosmic lighthouse where the rotating beam never sweeps past us, leaving only the blinding core visible. Simulations support this. Certain plasma densities can absorb lower energy emissions, effectively erasing the burst's afterglow from our instruments. But skeptics counter with an unsettling detail. The Vela Junior burst's energy profile didn't quite match any known gamma-ray burst model. Its spectra lacked the telltale signatures of matter-antimatter annihilation or neutron star mergers. Instead, it resembled theoretical predictions for a naked singularity, a black hole forming without an event horizon, a scenario so bizarre it defies Einstein's equations. While mainstream physics dismisses naked singularities as mathematical oddities, their hypothetical existence opens a Pandora's box. Gravitational anomalies where the laws of space and time break down completely. Could such an event have generated the burst while leaving no conventional aftermath? Then there's the wild card, primordial black holes. These hypothetical relics from the Big Bang, some no larger than atoms but as massive as mountains, could collide or evaporate unpredictably. If two such objects merged near the Vela region, their death throes might produce a gamma-ray flash without the usual stellar debris. The idea gains traction from the burst's location, far from any known galaxy, in a patch of intergalactic space where wandering primordial black holes might lurk unseen. The silence following the Vela Junior anomaly haunts astronomers to this day. Most bursts reward scrutiny with clues. This one taunts with its absence. Whether it was a plasma-shrouded catastrophe, a crack in reality's fabric, or something beyond our current physics, one thing is clear. The universe keeps a few secrets close, revealing just enough to remind us how much we have left to discover. And sometimes the most profound mysteries aren't what we see, but what we don't. The cosmos is supposed to expand evenly, like raisins in rising bread dough, every galaxy drifting apart from every other in a stately, predictable dance. But in 2008, astronomers studying the cosmic microwave background stumbled onto something that shouldn't exist. A handful of galaxy clusters hurtling in the same direction at nearly 1,000 kilometers per second, as if tugged by some unseen force. They called it dark flow, and unlike the orderly expansion of the universe, this was a current, a river of galaxies streaming toward a point beyond the observable horizon. The implications were staggering. Either our measurements were flawed, or something out there, something vast and invisible, was pulling on the fabric of space-time itself. At first, skepticism ran high. Could this just be an artifact of incomplete data or instrument bias? Yet repeated studies, including observations from NASA's Wilkinson microwave anisotropy probe, only cemented the anomaly. Dark flow wasn't local. It stretched across billions of light years, affecting clusters as far as we could see. And that raised an even sharper question. What could possibly exert gravity on such a scale? The leading culprit, a supermassive structure lurking in the unobservable universe, perhaps a gargantuan concentration of mass left over from the Big Bang, or even another universe bumping against ours in the multiverse foam. But without light or any electromagnetic signature, how could we ever detect it? This is where plasma whispers a tantalizing clue. galaxy clusters are swimming in ionized gas, and as they move, their charged particles interact with intergalactic magnetic fields, emitting faint radio waves. In theory, these emissions could map the flow's contours, revealing whether it's driven by gravity or something stranger. Some researchers suggest dark flow might trace the scars of a primordial asymmetry, a time before inflation when the universe's plasma wasn't perfectly uniform. Tiny fluctuations then could have snowballed into vast gravitational tides today. Others propose that dark flow isn't motion at all, but a shadow, a relic of our universe's violent birth, imprinted on space-time like a fingerprint. Then there's the wildest idea. What if dark flow is evidence of other universes? In certain multiverse models, neighboring universes could tug on ours through shared higher dimensional space, their gravity bleeding through like a hand pressing against a curtain. If true, the galaxy clusters aren't being pulled toward matter, but toward the gravitational wake of another reality entirely. Plasma emissions along the flow's path might hold the key, subtle distortions in polarization or synchrotron radiation patterns that betray an external influence. For now, dark flow remains a controversy. Some surveys claim to debunk it, others affirm it with ever sharper data. But whether it's a measurement error or a crack in cosmology's foundation, one thing is clear: the universe still has the power to unsettle. Dark flow challenges our belief that the cosmos is uniform, isotropic, knowable. And if galaxy clusters are indeed racing toward some unseen horizon, it's a reminder that the greatest mysteries aren't just in the stars, but in the voids between them. In the vast cosmic menagerie of strange signals, few are as beguiling as the whispers radiating from Hercules X1. This X-ray binary system, a neutron star locked in a deadly dance with a stellar companion, has long fascinated astronomers. But in 2015, it did something extraordinary. Instead of its usual rhythmic pulses, Hercules X1 emitted a series of quasi-periodic bursts, flickering like a malfunctioning beacon. These weren't the clean, predictable ticks of a cosmic clock. They stuttered, skipped, and occasionally flared with irregular intensity, as if something deep within the system's plasma-filled heart was stirring. The neutron star in Hercules X1 is no ordinary corpse of a dead sun. It's a highly magnetized powerhouse, siphoning material from its companion star at a frenetic pace. As that stolen gas spirals inward, it forms an accretion disk, a swirling maelstrom of superheated plasma. Normally, this process generates steady X-ray pulses as material slams onto the neutron star's surface at nearly light speed. But the 2015 anomaly was different. The pulses arrived in clusters, some bunched tightly together, others spaced apart inconsistently. Even stranger, their energy spectra. The fingerprint of their radiation shifted subtly between bursts, suggesting the plasma's behavior had changed in ways no model predicted. One compelling theory involves the accretion disk itself. Imagine a vast, turbulent ocean of plasma, whipped into violent eddies by the neutron star's gravity and magnetic field. Under normal conditions, this disk feeds the star's surface evenly, like water circling a drain. But occasionally, instabilities arise, perhaps triggered by clumps of denser material or magnetic reconnection, events where the plasma's flow becomes chaotic. These disruptions could create ripples in the disk, altering how and when material crashes onto the neutron star. The quasi-periodic pulses might be the cosmic equivalent of a stuttering engine, plasma hiccups reverberating through the system. Yet even this explanation leaves gaps. Some of the signal's irregular bursts lasted mere milliseconds, far too brief to be explained by disk instabilities alone. Another possibility points to the neutron star's magnetosphere, the region where its magnetic field dominates the surrounding plasma. If the field lines twisted or snapped, a phenomenon called magnetic reconnection, they could unleash localized explosions of energy, brief flares buried within the broader pulse pattern. This would account for the erratic spikes, but raises another question. Why didn't Hercules X1 exhibit this behavior before or since? The most tantalizing clue lies in the signal's polarization, the orientation of its light waves. Observations revealed that during the anomalous bursts, the X-rays were more strongly polarized than usual, a sign that the plasma had become unusually ordered, channeled by magnetic forces in a specific direction. This isn't just a detail, it's a smoking gun. Highly polarized emissions suggest the presence of a structured environment, perhaps a temporary jet or column of plasma funneled along magnetic field lines with freakish precision. Such structures are rare in X-ray binaries, and their appearance hints at hidden complexities in how plasma behaves under extreme conditions. For now, Hercules X1's whispers remain an enigma. Was this a one-off tantrum from a capricious cosmic engine or a glimpse of deeper physics at work? The system has since returned to its regular rhythm, but astronomers watch it closely, knowing that somewhere beneath the roar of its accretion disk, the plasma might stir again, and next time we'll be listening. The Andromeda Galaxy has been Earth's cosmic neighbor for billions of years, close enough that its spiral arms gleam in our night sky, yet distant enough to keep its secrets. But in May of 2015, for just 72 milliseconds, it broke its silence. A radio telescope in Sweden picked up an intense burst of emission from M31, the kind of signal that normally comes from billions of light years away. Yet this one originated a mere 2.5 million light years from Earth, practically next door in cosmic terms. And unlike the fast radio bursts that flicker from the distant universe, the Andromeda signal never repeated. It flashed once, vanished, and left behind a mystery that still defies explanation. What made this burst so baffling wasn't just its proximity or its brevity, it was the signal's profile. Fast radio bursts from deep space show a telltale dispersion, a smearing of their frequencies caused by traversing vast clouds of interstellar plasma. The Andromeda signal had virtually none. It was crisp, almost artificially clean, as if it had barely interacted with the sparse matter between galaxies. That alone ruled out most known astrophysical sources. Magnetars neutron stars with apocalyptic magnetic fields often produce similar bursts, but they repeat, and their signals bear the scars of plasma turbulence. This was a lone, unscathed shout in the dark. Astronomers scrambled to rule out terrestrial interference. Could it have been a satellite's rogue transmission or radar bouncing off space debris? The signal's frequency and polarization pointed decisively beyond Earth. Its radio waves were circularly polarized, a twist usually seen in powerful magnetic environments like pulsars or black hole jets, yet M31's core showed no unusual activity at the time. If the signal came from a compact object like a neutron star, why didn't it reappear? And why was there no X-ray or optical counterpart, the usual fingerprints of such violent events? The leading natural explanation invokes an exotic stellar corpse called a radio supernova, a dying star collapsing in a way that channels its energy into a focused radio burst rather than a visible explosion. But even this is a stretch. Radio supernovae are rare, and none on record have produced a burst this isolated or this intense. Another theory suggests a primordial black hole, a relic from the Big Bang evaporating in a final burst of Hawking radiation. These hypothetical objects could theoretically emit a single, powerful radio pulse as they wink out of existence. Yet without a second detection, the idea remains speculative at best. Then there's the whisper in the scientific community no one wants to amplify too loudly. The Andromeda signal's cleanliness, its one-off nature, and its unnerving proximity align eerily with what we'd expect from an artificial beacon. Not necessarily a messenger, just a fleeting blip like a radar ping or an energy surge from an advanced civilization's technology. It's a tantalizing thought, but also a cautionary one. The universe is under no obligation to conform to our expectations, and often the simplest answer isn't the most exciting. Years later, the Andromeda signal remains an enigma, a cosmic flashbulb that left no afterimage. Whether it was a stellar death cry, a black hole's swan song, or something far stranger, its legacy endures as a reminder. Even in our own galactic backyard, the universe keeps a few tricks up its sleeve. And sometimes the most profound mysteries aren't in the distant cosmos, but floating right in front of us, silent and unresolved. Boyajian star, officially known as KSE 8462852, already defied categorization with its erratic dimming, but when researchers turned their attention to the plasma whispers surrounding it, the mystery deepened. Unlike typical stars, this cosmic oddity didn't just flicker. It seemed to interact with the space around it, emitting faint radio signals that crackled like static from a half-tuned channel. Were these the murmurs of a chaotic dust cloud or something far more speculative, the hum of an alien megastructure siphoning energy from its host star? The dust cloud theory held early sway. Observations revealed micron-sized particles, likely debris from comets or collisions, orbiting the star in uneven swarms. When these clouds passed between Boyajian star and Earth, they'd block light in patchy, unpredictable ways, explaining the star's bizarre dimming patterns. But plasma added a twist. Dust alone couldn't account for the star's sporadic radio emissions, which pulsed with low-frequency energy suggestive of charged particles accelerating in magnetic fields. If the dust were mixed with ionized gasoplasma energized by the star's radiation, it could create a dynamic, electrically active environment. Picture a sandstorm where every grain carries a tiny charge, crackling with miniature lightning as it swirls. Such a scenario might explain both the dimming and the signals, but there's a catch. No known natural process produces plasma emissions this structured without an obvious driver, like a pulsar or black hole. Enter the megastructure hypothesis. Freeman Dyson once imagined advanced civilizations building vast energy collectors around stars, not solid shells, but loose constellations of orbiting panels or habitats. If something like that existed around Boyajian star, even partially completed, it might leave traces in the surrounding plasma. Solar panels on Earth, for instance, leak faint radio waves as a byproduct of operation. A Dyson swarm could theoretically do the same, its machinery ionizing nearby dust or generating electromagnetic interference as it harvested stellar energy. The star's radio signals, though weak, clustered at frequencies where such leakage might occur. Even more intriguingly, some of the dimming events matched spectral patterns inconsistent with pure dust, instead resembling the light-scattering properties of lightweight, optically thin materials, like those we might use in solar sails or energy-absorbing foils. Skeptics countered with cosmic Occam's razor. Why invoke aliens when plasma physics offers simpler answers? Boyajian star is young by stellar standards, prone to tantrums. Its flares could be ionizing nearby debris, creating temporary plasma halos that emit radio noise. Or perhaps we're seeing the aftermath of a planetary collision, where vaporized rock forms a conductive soup of charged particles, glittering with transient electrical activity. The star's location in the Milky Way's plane also raises the odds of foreground interstellar plasma distorting our observations, like static from a celestial radio jam. Yet the most compelling data came from the star's polarization, a subtle twist in its light waves hinting at magnetic influence. When plasma moves through a magnetic field, it can polarize light passing through it. Boyajian star's polarization signatures suggested its surrounding plasma wasn't just chaotic. It was organized as if shaped by unseen forces. Natural magnetic fields can create such order, but the degree of structure gave pause. Compare it to the difference between scattered campfire smoke and the precise trail of a rocket's exhaust. Both are plasma, but one implies design. The debate lingers because Boyajian star refuses to fit neatly into any box. Its plasma signals could be the death throes of a chaotic young system, or the birth pangs of something unimaginable, For now, it remains a cosmic Rorschach test, a blur of dust and energy where every observer sees what they dare to imagine. Whether natural or engineered, one truth emerges: the universe writes its riddles in plasma, and we're only beginning to learn the language. When Oumuamua streaked through our solar system in 2017, it shattered expectations. The first confirmed interstellar visitor wasn't a comet spewing gas or an asteroid tumbling silently. It was something in between, a reddish, elongated object that defied classification. But the real shock came when telescopes noticed it was accelerating, as if pushed by an unseen force. The explanation seemed obvious at first: outgassing, the same process that makes comets speed up as sunlight vaporizes their ices. Except Oumuamua left no visible trail of gas or dust, so if it wasn't a comet, what was nudging it forward? The answer might lie in one of the universe's most overlooked forces: plasma. At its core, plasma is just ionized gas, charged particles freed from their atoms. But in the right conditions, it becomes something more: a cosmic sculptor capable of shaping celestial objects in ways we're only beginning to understand. Oumuamua's acceleration could hint at a rare phenomenon, a plasma sail effect. Imagine solar wind, the stream of charged particles from the sun pushing against any conductive material in space. If Oumuamua's surface carried even a faint electric charge, that interaction could generate minute but measurable thrust, no outgassing required. Earth's own experimental plasma sails work on the same principle, harnessing solar wind for propulsion without fuel. The catch: Oumuamua was classified as rocky, not metallic, and most rocks are poor conductors. But what if its surface wasn't ordinary at all? Some researchers point to the object's peculiar reflectivity. Oumuamua's brightness varied dramatically as it spun, suggesting an irregular surface, perhaps one scarred by cosmic radiation over millions of years. In the interstellar medium, high-energy particles can transform organic-rich materials into a thin, conductive crust called a carbon mantle. This exotic coating, just microns thick, could theoretically interact with solar wind while remaining invisible to telescopes. Even more intriguingly, such a crust might form naturally on objects exposed to the harsh conditions between stars, making Oumuamua not an anomaly, but a prototype of a new class of interstellar wanderers. Then there's the wild card: magnetic fields. If Oumuamua carried residual magnetism, a fossil field locked into its structure during some ancient stellar explosion, it could have channeled plasma flows asymmetrically, creating uneven thrust. Picture a spinning top with one side slightly heavier. Over time, tiny forces add up. This would explain the object's acceleration without requiring visible outgassing or an artificial origin. But here's the puzzle: we've never observed a natural object behaving this way before. That either means Oumuamua is extraordinarily rare, or we've been missing a fundamental piece of plasma physics playing out in the darkness between stars. Skeptics, of course, argue for simpler explanations. Perhaps Oumuamua did outgas, but in ways our instruments couldn't detect: ultrafine dust or pure hydrogen ice, which leaves no visible trace. Or maybe its acceleration was statistical noise, an illusion caused by incomplete data. Yet the plasma hypothesis lingers because it bridges the gap between Oumuamua's rocky appearance and its comet-like behavior. It suggests a universe where even seemingly inert objects are engaged in silent dialogues with the charged particles around them, their motions dictated by forces we're only beginning to map. The stakes are higher than just one strange visitor. If plasma interactions can propel interstellar objects, they might be far more common than we thought: a hidden population of cosmic drifters, reshaped by their journey through the galaxy's electric winds. Every unexplained acceleration, every odd rotation we've dismissed as noise could be a clue waiting to be deciphered. Oumuamua's echo isn't just a mystery, it's an invitation to rethink how the universe moves when we're not looking. And the next time an interstellar guest arrives, we'll be listening not just for its shape, but for the whispers of the plasma that carried it here. The legend of the Black Knight satellite reads like a sci-fi thriller, an ancient alien probe silently orbiting Earth for millennia, occasionally beaming mysterious signals down to our planet. Stories claim it predates human spaceflight, that Nikola Tesla intercepted its transmissions in the 1890s, and that governments have been covering up its existence for decades. But peel back the layers of conspiracy, and you'll find something far more fascinating: the real cosmic phenomena hiding behind the myth, where plasma and radio echoes conspire to create shadows of something that was never there. At the heart of the Black Knight lore are radio signals, erratic, unidentifiable pulses recorded by early space missions and amateur radio operators, the most famous example. Strange echoes picked up during the 1960s by Project Gemini astronauts, described as unusual interference with no obvious source. These weren't alien greetings, they were the whispers of Earth's own plasma shield. The ionosphere, that layer of charged particles surrounding our planet, acts like a funhouse mirror for radio waves. Transmissions from the ground or satellites can bounce off it, distorting into delayed, ghostly repeats that sound anything but natural. Add to that the Van Allen radiation belts donuts of high-energy plasma trapped by Earth's magnetic field, and you've got a recipe for cosmic misdirection. Signals ricochet, frequencies smear, and what begins as a routine communication ends up sounding like a cryptic broadcast from the void. Then there's the object itself. The grainy photos purportedly showing the Black Knight. Most are space-age debris, thermal blankets lost during shuttle missions, or discarded satellite parts tumbling in orbit. But here's where plasma steps in again. When sunlight hits certain materials in space, it can ionize surface atoms, creating a transient plasma sheath that alters how the object reflects radar or emits radio noise. This isn't just theoretical. The International Space Station has observed similar effects on its own hardware. A piece of space junk shimmering with plasma could easily be mistaken for something far more sinister, especially through the lens of mid-century technology straining to interpret the unknown. The final nail in the Black Knight's coffin comes from modern astronomy. If an alien satellite had been orbiting Earth for centuries, even stealthily, our current networks of radar and optical telescopes would have spotted it. Instead, every anomaly attributed to it has been debunked, either as space debris, atmospheric phenomena, or good old-fashioned hoaxes. Yet the legend persists, and that's the real lesson here. The universe doesn't need aliens to be strange. Plasma physics alone can conjure echoes that defy intuition, bending radio waves into shapes that tease our imagination. So the next time you hear a story about mysterious orbital signals, remember, the truth isn't always hidden. Sometimes it's just floating in plain sight, wrapped in the electrified embrace of Earth's own plasma cloak. And that, in its own way, is stranger than any myth. Rising like colossal hourglasses from the Milky Way's core, the Fermi bubbles stretch 25,000 light-years into the void, twin towers of searing plasma that defy everything we thought we knew about our galaxy's heart. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these gargantuan structures glow in high-energy gamma rays, but it's their radio whispers that truly unsettle. Unlike the chaotic static of most cosmic phenomena, the bubbles emit synchrotron radiation, a eerie hum of electrons spiraling near light speed through magnetic fields. This isn't just background noise, it's the signature of something violent, something ancient, and something we still can't fully explain. The mystery lies in the plasma itself, a soup of charged particles hotter than the surface of stars. Normally, such energetic emissions come from discrete sources, supernova remnants or quasar jets, but the Fermi bubbles aren't confined. They're a diffuse, almost ethereal presence, their radio waves painting the sky with a uniformity that suggests a single cataclysmic event. The leading theory, a past eruption from Sagittarius, a star, the supermassive black hole at our galaxy's center. Picture a belch of cosmic proportions. Millions of years ago, the black hole might have devoured a star or gas cloud, unleashing a jet of plasma so powerful it punched through the Milky Way's disk, inflating these bubbles like cosmic balloons. Yet even this dramatic scenario struggles to account for the synchrotron radiation's odd consistency. If the bubbles were born from a chaotic outburst, why do their radio waves lack the expected turbulence? Then there's the enigma of the bubble's edges, shockingly sharp, as if sculpted by an invisible hand. Synchrotron emissions usually fade gradually, but the Fermi bubble's boundaries are crisp, suggesting their plasma is somehow contained, like steam trapped under glass. One provocative idea involves dark matter. If the Milky Way's halo of invisible particles interacts weakly with the plasma, it could act as a barrier, shepherding the bubbles into their precise geometry. It's a stretch, but not impossible. Dark matter's gravitational influence is the only force we know of that could corral such energetic material without leaving a visible trace. The most tantalizing clue, though, comes from the bubble's polarization. Recent observations reveal their radio waves are partially polarized, meaning they're not just random noise, they've been organized by magnetic fields. This is where plasma's dance with magnetism gets weird. The Milky Way's magnetic field is a tangled web, yet the bubble's polarization suggests large-scale order, as if the field lines were combed straight by the eruption that birthed them. Imagine blowing smoke rings through a maze of spider silk. The rings shouldn't emerge perfectly aligned, yet somehow these did. What does it all mean? The Fermi bubbles might be a fossil record of our galaxy's violent youth, a relic of a time when Sagittarius, a star, was anything but quiet. Or they could hint at something far stranger, a recurring cycle of eruptions, or even evidence of dark matter's hidden interactions. For now, their radio whispers remain a cipher, a reminder that even our own galactic backyard holds mysteries as deep as any in the cosmos. And every new observation peels back another layer, revealing not just how the universe works, but how little we truly know. In the quiet static between galaxies, where darkness should reign undisturbed, radio telescopes in 2020 caught something bizarre, a faint, fluttering signal that seemed to pulse from the void itself. Dubbed the Dragonfly Anomaly, this whisper of radio waves didn't match any known cosmic object. Instead, it flickered with a rhythm that hinted at something far stranger, the invisible hand of dark matter brushing against the fabric of the universe. What set Dragonfly apart wasn't just its origin, a nondescript patch of sky far from any known galaxy, but its peculiar spectral signature. Most radio emissions from deep space are messy, smeared by their journey through turbulent plasma. Dragonfly's signal was oddly clean, as if it had slipped through the cosmos unscathed. Even more intriguing, its frequency drifted subtly over time, a telltale clue that whatever produced it was moving fast. Not star-fast or galaxy-fast, but something closer to the velocity of dark matter itself, the elusive, invisible substance that makes up 85% of the universe's mass. Theories erupted like sparks in a vacuum. One camp proposed actions, hypothetical dark matter particles that, in the presence of strong magnetic fields, could transform into photons, the very radio waves we detected. Picture a cosmic alchemy where invisible particles morph into detectable light as they traverse galaxy clusters' magnetized plasma. If true, Dragonfly might be our first glimpse of dark matter's hidden interactions, a shadow language finally translated into something we can hear. But skeptics pointed to plasma's capacity for deception. Intergalactic space isn't entirely empty. It's threaded with diffuse ionized gas, and under rare conditions, this plasma can amplify or distort background radiation into artificial-looking signals. Could Dragonfly be a mirage, a ripple in the cosmic pond, magnified by some unseen lens of plasma? The signal's transient nature supports this. It vanished as suddenly as it appeared, leaving no trace in follow-up observations. Yet the absence of a visible lens or foreground object keeps the mystery alive. Then there's the wild card primordial black holes, these hypothetical remnants of the Big Bang, some no heavier than asteroids, could lurk in the spaces between galaxies. If one passed through a magnetized plasma cloud, its gravity might twist the surrounding magnetic fields, unleashing a burst of synchrotron radiation, a fleeting radio chirp before fading back into the dark. Dragonfly's drift and abrupt departure align eerily with this idea, though the odds of catching such an event are astronomically slim. The debate rages because Dragonfly straddles the line between revelation and cosmic coincidence. If it was dark matter, it's a Rosetta Stone waiting to be decoded, proof that the universe's dominant substance isn't entirely mute. If not, it's a reminder of how plasma and magnetism can conspire to mimic the impossible. What lingers is the tantalizing question: was Dragonfly a one-off glitch or the first note in a symphony we're only beginning to hear? Until another signal surfaces, we're left listening to the static, wondering what other whispers might hide in the dark. The universe is playing a cosmic shell game with its own matter, and we're only beginning to figure out where it's hidden. For decades, astronomers have faced a glaring discrepancy: about a third of the universe's baryonic matter. The protons and neutrons that make up stars, planets, and us simply can't be accounted for. But scattered throughout the static of unexplained radio signals, there are whispers of this missing material, concealed in vast, searing filaments of plasma threading the space between galaxies. These aren't just cosmic afterthoughts, they're the universe's hidden scaffolding, and their faint radio murmurs might finally reveal where the missing matter has been hiding all along. Picture the cosmos as a web, its strands not silk but ionized gas plasma heated to millions of degrees, stretched into tendrils thinner than a human hair yet spanning millions of light years. These filaments, predicted by simulations but maddeningly elusive, should contain most of the missing baryons. The problem, they're nearly invisible. Unlike stars or glowing nebulae, this plasma doesn't emit much light. But when galaxies interact or black holes erupt, they can send shockwaves through these filaments, making them briefly ring with radio emissions. It's like striking a tuning fork in a soundproof room. The vibrations are there if you know how to listen. That's where the unexplained signals come in. Some of the strangest radio detections, like the chime anomalies with their inconsistent dispersion measures, align eerily with predicted filament locations. Their odd frequency shifts and scattering patterns match what you'd expect if radio waves were traversing these ultra-thin plasma strands, where even a wisp of charged particles can distort signals in peculiar ways. The filament's extreme temperatures also solve another puzzle: why the missing matter doesn't collapse under gravity. At 10 million degrees, plasma moves too fast to clump, remaining diffuse enough to evade traditional telescopes, yet dense enough to nudge passing radio waves off course. But the real breakthrough came when astronomers combined radio data with X-ray observations. The faint glow of oxygen ions in X-ray surveys traces some filaments, but others only reveal themselves through their imprint on passing signals. One such clue arrived in 2018, when a team studying fast radio bursts noticed subtle, consistent delays in certain bursts' arrival times. These weren't random. They hinted at encounters with structured plasma, possibly the filaments themselves. The delays matched simulations of radio waves skimming the edges of these cosmic threads, their paths slightly bent by the ionized gas. It was like mapping invisible rivers by watching how leaves drift downstream. Yet mysteries remain. If filaments are so pervasive, why don't all radio signals show these distortions? The answer might lie in the filament's clumpy, uneven nature. Like fog patches on a highway, some signals pass through cleanly, while others hit dense knots of plasma and scatter wildly. This could explain why some bursts arrive crisp and others fragmented, a cosmic game of chance where the medium itself reshapes the message. The search for missing baryons isn't just bookkeeping, it's a test of whether we truly understand the universe's structure. Every unexplained signal that aligns with a filament's expected path is another thread pulled in the cosmic tapestry, revealing where the ordinary becomes extraordinary. And as telescopes grow more sensitive, we might finally hear the universe's hidden matter speaking not in shouts, but in the quiet, persistent hum of plasma vibrating between the stars. For decades, the Pioneer anomaly haunted physicists like an unsolved equation. Between 1980 and 2002, NASA Pioneer 10 and 11 spacecraft hurtling toward the edges of our solar system experienced a tiny but persistent deceleration, as if an invisible hand were gently tugging them backward. The force was minuscule, just 9.8 billionths of a meter per second squared, but it defied all predictions. At first, scientists scrambled to revise gravity itself, whispering about exotic dark matter or modifications to Einstein's theories. But what if the answer wasn't buried in the fabric of space-time, but floating in the charged soup of plasma surrounding our solar system? The key lies in something unexpected: heat. Pioneer's radioisotope thermoelectric generators emitted warmth as they powered the probes, and that heat radiated unevenly from the spacecraft's asymmetrical design. For years, this was dismissed as negligible until physicists realized the implications. In the near vacuum of space, even a faint temperature difference can ionize sparse interstellar particles, creating a microscopic plasma halo around the craft. When charged particles interact with a spacecraft surface, they generate a subtle but measurable force known as the plasma drag effect. Picture wading through a pool where the water clings to your skin. Pioneer might have been swimming through an invisible current of ionized gas, its own heat creating the very drag slowing it down. Critics initially balked. After all, the solar system's plasma density is vanishingly low. But here's the twist: Pioneer's trajectory took it through the Helios sheath, a turbulent borderland where the solar wind collides with interstellar plasma. In this region, charged particles are compressed and energized, forming a patchy but conductive medium. Even a whisper-thin plasma could exert cumulative force over decades, especially on a spacecraft emitting heat in lopsided bursts. Computer models later confirmed that anisotropic thermal radiation, fancy jargon for heat leaking unevenly, could account for up to 70% of the anomaly when combined with plasma interactions. The real clincher, New Horizons, humanity's fastest outbound probe, hasn't experienced anything like Pioneer's slowdown. Why? Its design radiates heat more symmetrically, and it carries less power-hungry equipment, minimizing plasma-generating temperature gradients. Meanwhile, modern probes like Voyager, traveling through different plasma conditions, show no comparable drift. It's as if the universe handed us a control group, proving the anomaly wasn't universal, just situational. Yet the Pioneer anomaly's legacy isn't just about solved puzzles. It's a masterclass in how easily we mistake plasma's subtlety for fundamental physics. Those 9.8 billionths of a meter, they weren't a crack in general relativity, just a whisper from the electrified ocean we're all swimming through. The cosmos rarely bends to our expectations, but sometimes the most profound revelations come from recalibrating our ears to its quietest murmurs. The cosmic microwave background, our universe's baby picture, should be smooth, a near-perfect snapshot of primordial plasma cooling into existence. But there's a blemish in this cosmic portrait, the cold spot, a vast, eerie void where temperatures dip inexplicably lower than anywhere else in the sky. Stretching over 1.8 billion light-years, this anomaly defies standard cosmology. Is it a scar from the Big Bang's turbulent birth, a ghostly imprint of another universe brushing against ours, or something even stranger? Hidden within its chilling silence, radio telescopes have detected whispers that only deepen the mystery. At first glance, the cold spot's explanation seemed straightforward. A supervoid, a region of space emptier than average, where the lack of galaxies and matter would subtly cool light passing through it. But when astronomers mapped the area, they hit a wall. The void's observed depth couldn't account for the temperature drop. The numbers simply didn't add up. That's where plasma enters the equation. Between galaxies, the interstellar medium isn't truly empty. It's a sea of ionized gas, charged particles so sparse they're nearly invisible, yet dense enough to sculpt the journey of light. If this plasma were clumped in just the right way, structured into vast, bubble-like filaments or nested voids, it could magnify the cold spot's cooling effect, bending and redshifting cosmic microwave photons as they traverse these unseen currents. Radio observations support this. Faint synchrotron emissions suggest magnetic fields threading the void, their presence hinting at plasma's invisible architecture. Yet the wildest theories dare to look beyond our universe. Some cosmologists propose the cold spot is a bruise, a collision with another universe during the brief, hyper-inflating moment after the Big Bang. In this scenario, the spot's coldness isn't just a lack of heat. It's a fingerprint of energy draining into a neighboring cosmos through a quantum tunnel. If true, the void's radio signatures might carry distortions unlike anything else in the sky, subtle polarization, twists or anomalous frequencies betraying the boundary of another reality. The idea straddles the line between physics and philosophy, but it's testable. Certain plasma-driven radio echoes, if ever detected, would align with models of universe-to-universe leakage. Skeptics counter with Occam's razor. Couldn't the cold spot just be a statistical fluke, a cosmic roll of the dice in an infinite tapestry? Maybe, but the odds are steep, around 1 in 50, that randomness alone could produce something this extreme. Others suggest a more exotic, yet still local, culprit, a texture defect, a wrinkle in spacetime's fabric left over from the universe's rapid expansion. These hypothetical kinks would warp spacetime itself, leaving cold imprints as they decay. The smoking gun, precise radio telescope arrays might catch the relic gravitational waves such an event would have unleashed, ripples still echoing through the plasma of intergalactic space. What makes the cold spot so compelling isn't just its existence, it's the way it refuses to fit neatly into any box. Whether a plasma-filtered mirage, a multiverse's calling card, or a quantum fossil, it's a reminder that even our most refined models of the cosmos are provisional. Every anomalous signal, every unexplained chill is a nudge to look deeper, because sometimes the universe's quietest corners speak the loudest truths. Gamma-ray bursts are supposed to be the universe's flashbangs, violent, blinding explosions that announce the birth of black holes or the collision of neutron stars with a blaze of light across the spectrum. Yet somewhere in the depths of space, there are bursts that break the rules, flashes of gamma rays so fleeting and faint, they leave no trace behind, no afterglow in X-rays. No lingering optical light, just a sudden spike on a detector, then nothing. Astronomers call them naked or ghostly bursts, and their existence hints at a cosmic conjuring trick where plasma itself becomes the ultimate cloaking device. Take SHGb02+14a, detected in 2023. This burst erupted with the energy of a supernova, but when telescopes swiveled to catch the expected afterglow, they found only darkness. It wasn't an equipment malfunction. Other bursts that night were captured perfectly. This one had simply vanished, as if something between us and the explosion had swallowed its light whole. The leading suspect, a thick shroud of magnetized plasma, dense enough to absorb lower energy emissions like optical and X-rays, while allowing only the highest energy gamma rays to slip through. Picture a cosmic filtration system where plasma acts like a one-way mirror for radiation, tuned to only let the most violent photons pass. The physics behind this is as elegant as it is eerie. When gamma rays travel through ionized gas, they can scatter off free electrons in a process called Compton scattering. Normally, this just dims the light slightly. But in environments where plasma is both extremely dense and threaded with powerful magnetic fields like the turbulent regions around newborn black holes, the effect becomes extreme. Lower energy light gets trapped, its photons bouncing endlessly in the charged soup until they're absorbed, while gamma rays punch through like bullets through fog. The result, a burst that telegraphs its violence in gamma rays alone, leaving astronomers with half a signal and a puzzle where the rest should be. But why would some bursts be shrouded while others blaze unobscured? The answer may lie in the messy nurseries where these explosions are born. Short gamma-ray bursts, typically caused by colliding neutron stars, often occur in chaotic, plasma-rich environments, regions littered with debris from stellar deaths or swirling with magnetic fields twisted to breaking point. If the burst occurs inside a dense plasma cloud, perhaps the remnants of a recently shattered star, the surrounding ions could act like a cosmic muffler, smothering the aftermath while the initial gamma rays escape. It's the difference between a firework exploding in open air versus underwater. One lights up the sky, the other vanishes with a muted flash, the most tantalizing twist. Some ghostly bursts might not be ghosts at all, but cosmic mirages. Simulations suggest that under the right conditions, plasma lenses could focus gamma rays toward Earth while bending other wavelengths away, creating the illusion of an afterglow-less burst. This would require precise alignment, a filament of plasma curved just so, like a magnifying glass floating in space, but in a universe this vast, statistical inevitability means it's bound to happen occasionally. The implication is staggering. We might be missing entire populations of gamma-ray bursts simply because their light is being warped and filtered before it reaches us. For now, these phantom bursts remain outliers, whispers in a catalogue of cosmic screams. But with every new detection, they challenge our assumptions about how energy moves through the universe. Plasma, often dismissed as the background static of space, reveals itself as a master illusionist, capable of hiding entire cataclysms in plain sight. The lesson is clear. Sometimes the universe's most violent secrets aren't in what we see, but in what we almost missed. In the quiet static of routine sky surveys, some signals refuse to fade into anonymity. One such enigma arrived in 2011 when the Allen Telescope Array, a field of radio dishes in Northern California dedicated to the search for extraterrestrial intelligence, caught a whisper at exactly 1420 megahertz. This wasn't just another blip in the cosmic noise. It was a narrowband signal, razor-thin in frequency, parked precisely on the hydrogen line. The universal radio channel scientists had long hypothesized an advanced civilization might use to announce itself. Dubbed ATA-1's unidentified line, this transmission lasted a full 30 seconds before vanishing, leaving behind a trail of unanswered questions and a debate that still simmers today. What made this signal so compelling wasn't just its frequency, though that was provocative enough. The hydrogen line at 1420 megahertz is a sacred number in astronomy. It's the emission frequency of neutral hydrogen, the most abundant element in the universe, and a natural meeting point for any civilization trying to communicate across the stars. But ATA-1's signal wasn't just near this frequency. It was pinned to it with almost unnatural precision, drifting less than 1 hertz over its half-minute duration. Natural cosmic processes like pulsars or masers can't maintain that kind of stability. Even human-made satellites typically exhibit slight frequency wobbles. This was a signal so clean it seemed engineered, yet the real mystery lay in its origin. Initial tracking pointed toward the vicinity of Kepler-44, a star system 1,600 light-years away hosting at least one known exoplanet. But here's the catch. Kepler-44's planet is a hot Jupiter, a gas giant orbiting lethally close to its sun, hardly a hospitable place for life as we know it. Could the signal have come from somewhere else along that line of sight? Possibly. The Milky Way's disk is littered with stars, and without a precise distance measurement, the true source remains a cosmic needle in a haystack. Follow-up observations turned up nothing, no repeat transmissions, no secondary frequencies, just silence. Skeptics were quick to offer alternatives. Might this have been a secret military satellite, its transmissions momentarily bleeding into a frequency usually reserved for astronomy? The United States Air Force has never confirmed such activity, and the signal's hydrogen line specificity feels oddly coincidental for a clandestine operation. Others suggested a rare form of radio interference called sporadic E, where Earth's ionosphere temporarily reflects distant terrestrial signals skyward, creating ghostly echoes. But sporadic E typically distorts frequencies, whereas ETA-1's signal was pristine. Then there's the tantalizing, if controversial, possibility that we caught a fleeting moment of something far more profound. Imagine a civilization's beacon sweeping the galaxy like a lighthouse beam, its signal so brief that catching it requires being in the right place at the exact right millisecond. Or perhaps a defunct probe, its dying transmitter finally giving out after millennia adrift. The signal's 30-second duration is oddly reminiscent of the Arecibo message, humanity's own 3-minute broadcast to the stars in 1974. Could this have been someone else's version, cut short? 12 years later, the ETA-1 signal remains an open case. It's a reminder that for all our advances, the cosmos still holds moments of sheer unpredictability, signals that tease the boundary between natural wonder and deliberate design. And while Occam's razor favors the ordinary, the universe has a habit of surprising us. Until another signal like it appears, we're left with a quiet but persistent question. Was that 30 seconds of static just a cosmic coincidence, or the first note of a conversation we weren't meant to hear? From the wow signals haunting one-off bursts to the eerie synchronicity of chime anomalies, these 25 cosmic whispers share one unsettling thread. They all pass through the seething, unpredictable plasma that fills the voids between stars. This isn't empty space, it's an electrified labyrinth, a filter that distorts, amplifies, and sometimes even mimics signals in ways we're only beginning to understand. Plasma doesn't just carry these messages, it reshapes them, turning straightforward physics into riddles that defy categorization. Consider how many of these signals, like FRB 121102's repeating cadence or the Andromeda signal's uncanny cleanliness, seem to dance on the edge of plausibility. Could natural processes alone really produce such precision? Or does plasma, with its capacity to twist radio waves into deceptive patterns, merely make them appear artificial? The same ionized soup that birthed stars might also be the universe's greatest illusionist, scattering clues like breadcrumbs leading us in circles. Even the most mundane explanations crumble under scrutiny. Take the Puritans. For years, their cosmic masquerade had astronomers chasing interstellar ghosts, only to find a microwave oven in an observatory kitchen. But for every Puritan debunked, there's a glimpse C01 or a Vela Jr. anomaly, enigmas that resist even our most creative theories. Yet the real fascination lies in the questions these signals refuse to answer. Are we listening to the death throes of magnetars, the whispers of dark matter, or dare we speculate the faint echoes of intelligence we don't yet recognize? The universe isn't obligated to fit our expectations, and that's what makes this search so thrilling. Every unexplained signal is a crack in the doorway of the unknown, inviting us to push harder, listen closer, and question everything. So what do you think hides in the static, a cosmic symphony we've yet to decode? A language written in plasma and light, or something beyond our current imagination? The comments are open and the conversation is just beginning. After all, the greatest discoveries start with a single, unshakable question.